There is a material sitting inside every AI chip, every server processor, and every GPU driving the artificial intelligence revolution, and almost nobody talks about it. Not the transistors, not the logic, not the memory, the substrate. The base layer that holds everything together, routes every signal, and carries every electron between the billions of components packed into a modern chip package. For decades, that substrate has been made from the same material. Organic resin. A plastic. The same basic chemistry that goes into a circuit board in a 1990s desktop computer. Refined and compressed down to microscopic tolerances, but fundamentally the same stuff. That material is now breaking. Not metaphorically. Literally, the thermal loads from kilowatt-class A-wine chips are warping organic substrates, cracking solder joints, and throttling performance in ways that no amount of cooling can fix. The physics of organic resin has hit its wall, and the industry that built the world's most advanced computing hardware on top of that material is looking for a replacement. China just declared it found one. And the country it is threatening to displace is not the one you might expect. If this is the kind of story you track the material shifts underneath the semiconductor industry, subscribe before we go further. The glass substrate race is moving fast, and the next chapter is already being written. To understand why glass changes everything, you need to understand what a chip substrate actually does. The word substrate makes it sound passive, almost irrelevant. It is not. When engineers build a modern AI chip, they are not building a single piece of silicon anymore. They are assembling a system. A GPU like Nvidia's B200 Blackwell contains multiple silicon dies, logic, memory, I/O, all mounted on a common carrier and connected by thousands of microscopic wires. The substrate is that carrier. It holds the dies in precise alignment. It routes signals between them at speeds measured in hundreds of gigabits per second. It distributes power across a chip drawing more than a kilowatt at full load. And it has to do all of this while maintaining dimensional stability measured in single-digit micrometers. Across a package that can be larger than a human palm, running continuously at temperatures that would destroy most electronic components. Organic substrates, the resin-based materials that have done this job since the 1990s, have one structural flaw. Their coefficient of thermal expansion does not match silicon. When a chip heats up, the silicon die expands at one rate. The organic substrate beneath it expands at a different rate. That mismatch creates mechanical stress. In a processor running at 50 watts, that stress is manageable. In an AY accelerator running at 1000 watts, the power level of chips now shipping into data centers, that stress is not manageable. It warps the substrate. It fractures the microscopic solder connections between the die and the carrier. It limits how densely connections can be packed, how fast signals can travel, and ultimately, how powerful the chip can be. The semiconductor industry has known this problem was coming for years. The theoretical solution has also been known for years. Replace the organic resin with glass. Glass matches silicon's thermal expansion coefficient far more closely than organic resin. Glass is flatter, harder, and more dimensionally stable under heat. It can be made thinner without warping. Glass allows signals to travel with lower dielectric loss, meaning less energy wasted as heat, more signal integrity at high speeds. And glass can be drilled with microscopic vertical channels called through-glass vias, or TGVs, that allow connections between layers of a package at densities organic substrates cannot approach. The physics of glass substrates is not in dispute. What has been in dispute for 20 years of semiconductor research is whether glass can actually be manufactured at the precision and yield rates that chip packaging demands. The transition from display-grade glass to semiconductor-grade glass looks like a single step on paper. In reality, it is two levels of difficulty apart. Semiconductor packaging requires surface flatness, dimensional uniformity, and via precision that make the most advanced display panels look rough by comparison. That question is now being answered. And it is being answered in Hefei, in Shenzhen, in Beijing, and in a cluster of former display factories that China has been quietly converting for the past 2 years. The company at the center of this story is BOE Technology Group. If you follow display technology, you know BOE is the world's largest LCD manufacturer. The Chinese company that dethroned Samsung and LG in flat panel production. The company that now supplies screens to Apple, Huawei, and virtually every consumer electronics brand on the planet. What BOE built to make those displays massive clean rooms, ultra-precision photolithography lines, thin film deposition systems that operate at nanometer tolerances across glass panels, measuring more than 2 meters on a side, turns out to be directly transferable to glass substrate manufacturing. The process logic of flat panel display manufacturing and glass core substrate manufacturing overlap at every critical step. Photolithography, thin film deposition, etching, chemical cleaning, dimensional inspection. Engineers who spent careers perfecting display glass at BOE did not need to learn a new discipline. They needed to apply existing mastery to a new application. That institutional knowledge transfer is the structural advantage no South Korean or American company can replicate quickly. You cannot build 20 years of institutional knowledge in 2 years, regardless of how much capital you deploy. BOE invested in its first glass substrate pilot line in 2024. By the first half of 2026, it had deployed a fully automated production line. In July 2026, BOE completed the full process flow for 20-layer large-size glass car substrates, the configuration required for the most advanced AI chip packages, and announced an acceleration of co-packaged optics development in partnership with Corning, the American glass specialist that supplies material to Apple and has been researching semiconductor-grade glass for years. Current monthly production capacity at BOE is estimated at 300 wafers. The ramp to 1,000 wafers per month is projected by the end of 2026, with gradual expansion into 2027. BOE is not alone. Visionox, one of China's 3 largest display manufacturers, announced a 5 billion yuan investment, approximately $700 million in glass substrate production earlier in 2026, and has been building out its materials and equipment supply chain since the second half of 2025. WG Tech, through its wholly owned subsidiary TGV Tech, achieved a through glass via process with an aspect ratio of 100:1 and a minimum via diameter of 5 micrometer specifications, matching the most demanding packaging requirements in the industry. WG Tech has already delivered glass substrate samples for 1.6 terabit optical modules to customers. Sky Semiconductor surpassed 20,000 units in wafer-level packaging shipments using TGV technology and achieved a breakthrough in 4-micron via diameter technology in 2024. Guangdong Fuzhixin Microelectronics was among the first Chinese companies to achieve mass production in glass panel level fan-out packaging. The supply chain is expanding beyond the chip makers. Hans Laser completed the development of TGV laser micromachining, equipment for semiconductor packaging, and has shipped panel-level glass substrate via drilling equipment, meaning China is now producing not just the glass substrate itself, but the specialized laser tools that drill the microscopic channels inside it. DR Laser has also completed TGV laser equipment development. Over 10 Chinese companies are now active across the glass substrate supply chain, spanning display manufacturers, PCB producers, packaging houses, and equipment makers. China officially declared 2026 the first year of large-scale glass substrate production. That is not marketing language. It is a policy directive backed by capital allocation across an entire industrial ecosystem simultaneously. The numbers behind the glass substrate market explain why China is moving with this urgency and why the incumbents it is targeting are watching with genuine concern. The global glass substrate market stood at roughly $240 million in 2026. That number is about to change dramatically. TrendForce projects the market will reach $8.5 billion by 2028. Sigma-Intel Consulting projects it could reach $27.6 billion by 2030. The compound annual growth rate between 2028 and 2040 is projected at 67.2%. For reference, the entire global flat panel display market generates roughly $150 billion per year. The glass substrate market, on those projections, approaches comparable scale in less than a decade, while requiring far more precision manufacturing, commanding far higher margins, and sitting at the center of the AI infrastructure build-out. BOE's market capitalization surged by over 100 billion yuan, approximately $14.7 billion in a single month in 2026, driven by a memorandum of understanding that contained no order value, no timeline, and no commercialization plan. The market was not reacting to current revenue. It was pricing in the trajectory. The incumbents China is entering this race against are not primarily American. They are South Korean. And that distinction matters for how this competition plays out. SKC, the South Korean chemical company, holds the most advanced commercial position through its subsidiary Absolix. Absolix completed installation of major equipment at its glass substrate factory in Covington, Georgia, and has begun providing mass production samples to customers including AMD. Entering the customer certification stage, the step that matters most in chip packaging, because qualification cycles take 18 to 24 months to complete. Samsung Electromechanics is running a pilot line in Sejong with mass production targeted after 2027. LG Innotek is collaborating with global clients on glass core technology development. The South Korean industry has explicitly adopted a vertical integration strategy designed to build customer certification barriers during the commercial window of 2026 and 2027. The logic behind that strategy is sound. Whoever gets their glass substrate qualified inside AMD's, Intel's, or Nvidia's packaging process first will have a durable lead. Chip packaging qualifications are not switched casually. They take years to complete and years to redo. First mover certification advantage is real. What changes that calculation is what China is offering. Competitive pricing and manufacturing scale that the display industry spent 20 years developing. BOA runs clean rooms larger than most South Korean competitors' entire facilities. If glass substrates follow the cost trajectory of display panels, and the process overlap makes that trajectory plausible, China's structural manufacturing advantages will eventually compress South Korea's first mover margin, regardless of how aggressively the Korean consortium moves in the next 18 months. The Western response has been direct. Intel moved earliest. At CES 2026 in January, Intel officially transitioned glass substrate technology into high-volume manufacturing with the launch of its Xeon 6 plus Clearwater Forest processor, the first commercial chip to ship with a glass core substrate at production scale. That announcement was significant not just as a product launch, but as a market signal. Glass substrates are no longer a laboratory technology. They are a production requirement. In May 2026, Intel publicly demonstrated its glass substrate prototype for co-packaged optics applications, targeting commercialization by 2030. TSMC launched its COP-OS platform, a glass interposer architecture standardized on a 310 by 310 mm panel format in 2025, with pilot production expected in 2027 and mass production in the second half of 2028. TSMC's roadmap places glass core substrate commercial production after 2030. The detail worth sitting with is the BOE and Corning collaboration. In July 2026, the world's largest display manufacturer and the American glass material specialist jointly disclosed advances in glass-based optical interconnects. BOE completed the full process flow for 20-layer glass core substrates. Corning introduced its glass bridge fiber to photonic integrated circuit connector platform. These are not companies at the beginning of a discussion. They are companies disclosing results. The collaboration between a Chinese manufacturing giant and a Western material specialist working on the same substrate layer of the AI supply chain illustrates how this competition is less about China versus West and more about who controls the physical foundation of what AI hardware becomes. Now, the honest assessment, because this story, like every story in the semiconductor program, has real limitations that matter. The gap between display-grade glass and semiconductor-grade glass is substantial. BOE's automated production line, deployed in early 2026, is still in validation. Mass production of advanced glass core substrates for the most demanding AI chip applications is targeted after 2026, not today. Even Corning, which has arguably the deepest glass materials expertise on the planet, released samples in 2026 but has not announced a mass production timeline. The entire global glass substrate industry, Chinese, Korean, and American, is simultaneously in the laboratory verification and early sampling stage. Nobody has solved this at commercial scale yet. There is a supply chain dependency that BOE's own July 2026 strategy document acknowledged. Its fully automated production line relies in part on Western laser drilling equipment for the TGV process precision tooling that China cannot yet fully replace domestically. Hans Laser has shipped TGV equipment. DR Laser has completed development. But full supply chain autonomy in the precision equipment layer has not been achieved. A manufacturing program with this dependency has an exposure that matters, particularly given the December 2024 export control package that specifically targeted semiconductor packaging equipment. And the customer certification challenge is not trivial. Absolix, the South Korean leader, is in certification with AMD today. BOE's certification pipeline for leading Western chip companies is not yet publicly confirmed at the same stage. The first mover certification advantage is real, and it is not yet China's. Step back from the yield rates and the certification timelines, because this story connects to something that the component level coverage misses entirely. For 30 years, the substrate underneath every chip in the world was invisible. It was organic resin. It was stable, cheap, and dominated by Japanese and Taiwanese companies that nobody outside the industry had heard of. Nobody thought about it. Nobody wrote about it. It was infrastructure, in the truest sense the foundation beneath the foundation. Kilowatt-class AI chips made it visible by breaking it. And when the semiconductor industry looked for what came next, it found glass. It found a material with fundamentally better thermal properties, fundamentally better signal characteristics, and fundamentally better dimensional stability. A material that happens to be manufactured at massive scale in China. The display industry gave China 20 years of process knowledge, precision equipment, clean room infrastructure, and workforce expertise that directly transfers to the new battleground. That transfer is not hypothetical. BOE deployed an automated glass substrate production line in 2026 using the same process logic its engineers developed for LCD panels. Visionox is bringing the same institutional knowledge from display manufacturing into semiconductor packaging. The companies competing for the glass substrate market are doing so with capabilities built in a different industry entirely, and the country that happened to dominate that industry is now positioned at the entry point of what may be the next critical semiconductor material. China has not won the glass substrate race. The yield rates are not fully qualified. The precision equipment chain is not fully domestic. The customer certifications inside the leading chip companies are not yet confirmed at the commercial stage. But China has something no other country in this race has in the same combination: the world's largest display glass manufacturing infrastructure. A workforce that mastered the overlapping process logic over 2 decades. And a government that declared 2026 the commercial starting year and backed that declaration with coordinated capital expenditure across more than 10 companies simultaneously. The material beneath the chip is changing. The country that built the world's screens is building what comes next. Subscribe to Signal Leap if you want to follow this race as the results become visible. BOE's capacity ramp. WGTech's customer certification. The first commercial AI chip to ship with a Chinese glass core substrate. All of it is arriving before this decade ends. One question for the comments, because this is where the analysts genuinely disagree. Do you think China's display manufacturing advantage translates cleanly to semiconductor-grade glass substrates? Or is the precision gap between display glass and chip packaging glass large enough that South Korea's purpose-built certification approach wins the commercial race? Drop your answer below. What does this mean practically for the engineers, the chip companies, and the consumers at the end of the supply chain? At the engineering level, glass substrates unlock chip architectures that organic materials cannot support. Denser through substrate vias mean more connections between chiplets in a single package. Lower dielectric loss means faster signal transmission with less heat generated per bit transferred. Better thermal stability means chips can sustain higher sustained power loads without the substrate becoming a reliability failure point. The performance ceiling of A-line chips in 2028 and 2030 is not determined solely by the transistor node. It is determined by what the packaging can support. Glass substrates raise that ceiling. At the chip company level, the qualification of a glass substrate supplier is a multi-year commitment. Intel's decision to ship the Xeon 6 plus Clearwater Forest on a glass core substrate in January 2026 was not made in 2025. It was made years earlier, validated through thousands of thermal cycle tests, mechanical stress tests, and electrical characterization runs. The chip companies evaluating glass substrates today: AMD with Epsilon, Nvidia with its own evaluation programs, and Broadcom through its joint venture in Singapore with PowerTech, are making decisions whose commercial consequences will show up in product roadmaps 3 to 5 years from now. China's window to enter that qualification pipeline is not indefinitely open. It is open now, in 2026 and 2027, while the entire industry is simultaneously in evaluation mode, and no single supplier has established a dominant certified position. At the consumer level, the glass substrate transition will be invisible the same way the shift from ceramic to organic substrates in the 1990s was invisible. What becomes visible are the consequences. AI chips that run faster, cooler, and more reliably. Data centers that process more per watt. Inference costs that fall as hardware density improves. The material that nobody talks about determines the performance of the hardware that everyone uses. China understands this. The 5 billion yuan from Visionox. The fully automated BOE line. The WG Tech via diameter breakthrough. The Hans laser equipment shipments. The government declaration of 2026 as the commercial starting year. These are not isolated corporate decisions. They are coordinated investments in the substrate that will sit beneath every high-performance chip of the next decade. Made, a country that has read the physics, understood the market trajectory, and positioned its existing industrial base accordingly. The glass substrate race is not finished. It is barely started. The measurements that matter, yield rates, customer certifications, production cost per wafer, will be reported by Tech Insights, TrendForce, and the supply chain analysts who track these things with the same precision that the substrate manufacturers apply to their products. Those measurements will tell the real story of whether BOE's display expertise translates at a semiconductor scale, or whether South Korea's purpose-built approach holds the certification lead long enough to make it durable. What is already clear is that organic resin's 30-year run as the invisible foundation of every chip is ending. The AI era is too power-hungry, too thermally demanding, and too interconnect dense for the old material to hold. Glass is what comes next. And the country best positioned to manufacture glass at scale walked into this race carrying 20 years of expertise it built for an entirely different purpose. Subscribe to Signal Leap. The next chapter in this story will be written in a certification lab somewhere when an AY chip company signs off on a Chinese glass substrate for a processor that ships in 2028. We will cover it when it happens.